Good evening, everyone. Sorry about that. There was a little issue with the sound. I'm coming to you recorded. I'm sorry about that, but I had to go to a conference in Tallahassee and I was afraid during the travel time I would be late for class. So I have pre-recorded this Monday night 11/8 class, November 8th class. We will continue on in chapter 8 and I will post the links for the movie notes and current events under separate cover. You will see them. Okay, let's get going. When we finished up last time, we were in the middle of chapter 8. We talked about the Inuit people. We talked about the global distillation effect. We talked about the atmosphere. We stopped with the layers of the atmosphere and what happens in every layer of the atmosphere. And I won't go through this again because we spent a lot of time going through it in the last class. But if you have any specific questions on it, feel free to go back and ask me any questions that you like. But we did spend a lot of time on it before. So let's pick it up. We'll talk a little bit more. We were starting to talk a little bit about atmospheric circulation. And I was telling you that way back in the old days, people kind of knew already what way the winds went. And they knew that they could travel in certain direction using those winds, and they were trade winds. And we talked about Egayon, which is an old ship, was rebuilt. People were experimenting on traveling around the world with this to see how it was like to travel many years ago on these ships. We talked about the Coriolis effect, and we stopped. We got to this area about air pollution. Now we're getting into some actual, let's say, more heavy-duty science here, because there's going to be some names of chemicals and how they interact and react in the atmosphere. So this is the type of stuff you have to go through kind of carefully and make sure you understand it. And we're going to talk about two types of categories of air pollution. There's primary and secondary pollution. And the main difference between primary and secondary air pollution and air pollutants is primary pollutants are chemicals that are released directly from the source into the atmosphere and they don't change. So for instance, if carbon dioxide is released and it doesn't convert to anything else in the atmosphere, that's a primary pollutant. Hydrogen can be a primary pollutant. Almost anything can be. But sometimes when chemicals get up into the air, and you'll see this on the chart in a minute, they react with other chemicals up in the air. And even though they might have been a primary pollutant, now they become a secondary pollutant. You had some hydrogen, you had some chlorine molecules, they mixed together and became hydrochloric acid, HCl. You had some sulfuric acid. You had some, sulfur dioxide or sulfur trioxide up in the air. It mixed with some of those additional hydrogens I mentioned a minute ago, and then you get sulfuric acid, which is H2SO4. Look at this chart over here, you get the idea. Some of your primary air pollutants, carbon monoxide, carbon dioxide, sulfur dioxide, nitrogen oxide, nitrogen dioxide. Those are all primary pollutants. They're released like that, go up into the air by themselves. Hydrocarbons and particulate matter, which we'll talk about in a minute, are as usually primary pollutants as well. Secondary pollutants. So some of these things are already up in the air and they start reacting with each other. And you get things like nitrous acid and nitric acid, HNO2 and HNO3. You get hydrogen peroxide, the stuff you use for treating cuts, H2O2. Sulfur trioxide, H2SO4 I mentioned a minute ago, which is sulfuric acid, and PANS, I'm not going to go into at this moment. So most of these nitrates and nitrites and sulfites and sulfates are the salt version of it. And that's a chemical term. When there's an acid-base reaction, you end up with a salt. Okay. Now, these air pollutants, we're going to break them down further and look at them in a little bit more detail. So you have particulate matter. Particulate matter are suspended dusts and mists. There's usually some solid in them that are suspended in the atmosphere. And you've all seen this, you know, a bus goes by and you see that whoosh and all that junk and gunk comes out of the tailpipe. Well, a lot of the more dangerous pollutants are actually invisible. You cannot see them. Carbon dioxide, carbon monoxide, things like that. But there's also this particulate matter, which you do see. That's that sooty, blackish stuff that's suspended in the air. Sometimes it can be things that are quite natural, like soil particles. The wind blows along and you see all this soil and sand get suspended. Soot from things being burnt, lead from in the old days when cars burned gasoline with lead in them, asbestos. That's why you got to be careful, and I'll talk about this later on, When you knock down a building that's got asbestos in it, we have to do what's called containment so we don't release asbestos particles into the atmosphere. And the sulfuric acid droplets from burning different chemicals that we'll talk about in a little bit. And many of these particulate matters can have toxic or carcinogenic effects. They land on materials and cause the materials to erode and corrode. You'll see them on sides of buildings. And many buildings, they cleaned them up after many, many years of having pollution in the cities in London and in France. And they found the buildings were actually totally different color than they thought those buildings were because it had been 200 years since that soot had been removed. The Houses of Parliament was one. They weren't sure what the real color was until they removed all this gunk and junk that was from particulate matter and other air pollutants. So as they try to restore buildings and to their historical glory, so to speak, and they have reduced pollution in many areas, they find out that the color of those buildings was not really the original color. They've been discolored over the years because of what's happened with pollutions and pollutants in the air. Particulate matter can scatter and absorb sunlight. So sometimes the sun cannot break through it, and it's cooler and it's less light underneath. And the microscopic particles are more dangerous than larger particles because they can get deeper into our lungs. We'll see later what's called the PM10 standard. That's particles that are less than 10 microns, which is pretty small. They can go right into your lungs, into the alveoli, which are the working units of the lungs, and actually clog our lungs up. So that's why the EPA, that's been changed over the years. They made it even smaller now, but the original was a PM10 standard. And some of the things, the pollutants we're talking about are things like dust particles, parts of lead from places where they're still using lead in the gasoline, and sulfuric acid, which we talked about before, which is a secondary pollutant from different reactions that happen, as we saw over here, where you end up with sulfuric acid because you have various sulfur compounds mixed with the hydrogen in the air. So that's particulate matter. Then we move on to the NOxes and SOxes, as environmentalists call them with our great sense of humor, right? NOxes and SOxes, because there's more than one type. So since there's SO2 and SO3, it's SOxes. And because it's NO2 and NO, it's NOxes. So NOxes and SOxes. Occasionally I'll drop into that if I'm not paying attention because I'm usually from giving a lecture with a group that knows it, or I'll mention what it is and then I'll keep saying it because it's what sort of a shorthand for us environmentalists. So the NOxes are gases that are produced when nitrogens and oxygens molecules interact, usually during a combustion, a burning process. And these things are involved, and we'll see in a minute, in the production of photochemical smog and acid rain. The acid fog also, believe it or not. I'll show you some pictures of pollution areas that are polluted in a second. I've got to pull it up. And these things are associated with global warming and ozone depletion in the stratosphere. And when these things land, they can corrode metals and other materials. And over the years, that's what's happened. As pollution has increased, and you go back to Liverpool when they started burning stuff with mechanization in the 1700s, and this spread throughout the world, when this, whatever goes up has to come down, it mixes in with the rainwater and it rains back down, you get acid rain. Now, acid rain doesn't mean the rain is going to be strong enough to melt you like the Wicked Witch in the Wizard of Oz. Oh, I'm melting, I'm melting. But it means water should be around 7, which is neutral on the pH scale. Generally, it's going to have some minerals in it, so it's not going to be completely basic or completely acidic. I mean, it'll be slightly acidic or slightly basic. It won't be completely neutral, unless you're in the lab where you've deionized the water and you've removed whatever might be in the water. Then you're not going to have a real natural situation, but it will be slightly acidic or slightly basic. But in the environment where it's gotten polluted, and you're talking acidic, the lower down you go on the pH scale. The pH scale runs 0 to 14. 7 is neutral. Anything under 7 is acid. Anything over 7 is basic. The closer to 0 you get, the stronger the acid. So when you start seeing, like a 6.9, that's a little bit of mineralization. But when you start seeing a 1.2, that's very acidic. And that can kill things and infect their biological processes out in the environment. So that's nitrogen dioxide and nitric oxides. Nitrogen dioxide and nitric oxides are both primary pollutants, and we talked a minute ago about what the difference between primary and secondary pollutants were. Nitrogen dioxide, when you see it in the air, and you know it's not fog, because you'll see it's a reddish brown color. Nitric oxide, you won't be able to see because it's colorless. But that's when you see these clouds in the air and you go, that thing is red-brown. That's very indicative that there's a large amount of nitrogen dioxide, probably from burning coal out there. So that's nitric oxides, NOxes. And when we have the discussions about alternative fueled vehicles and what would be better in terms of fueling, we have to consider that some pollutants might actually increase when you use certain alternative fuels, might increase the levels of nitric oxides, the NOxes, and the SOxes. So that's one thing we always look at when you look at environmental pollution from in alternative fuel vehicles, when you think you're saving the environment, and you might not be, because by switching vehicles, you might actually increase the pollutants. Then you have sulfur oxides, which result from chemical interactions of sulfur and oxides and oxygens. These are, again, major role in acid rain. They can damage stone and corrode metals, and they affect your respiratory system. They both do. See, the top one aggravates asthma. This one affects your respiratory system. Now, that's why in a lot of cities, you look and you think things like marble are pretty heavy, pretty hard. But when rain falls on it, that's acidic, it can affect the marble. So some of these buildings that were made out of marble 200-300 years ago, you see pitting on it because of the sulfur oxides from pollutants. So your SO2s, colorless, but they have a strong odor. And sulfur trioxide is a secondary pollutant formed from all those additional oxygens mixing with the SO2 in the air. And these are also colorless gases. Now, let me see if I can pull up my pollution pictures. Hold on a second. I want to show those to you so you can see what we're talking about. The pollution, come on. Here. Oh, it always looks disembodied when I do this because I'm going to find it. Air pollution pictures. Here we go. Give me 1 second. Yeah, I got to switch. It doesn't let me open two at a time, so I got to stop one share and go to another. Hold on 1 second. Okay, let me see where I got to. There we go. Okay. This was New York City in 1966. One of the reasons people were complaining, and I told you before, when the EPA was formed and they started putting in pollution controls starting in the early 70s, one of the first things people noticed were air and water pollution, because you walked outside and saw something like this. Now, this is an aerial shot. It was taken from above, but you can see, and this was during the day, how much of the city you couldn't see very far because of all the air pollution that was in the air. This is Denora, PA, Pennsylvania, in the 1940s. They did a lot of coal mining, and you can see what it looked like. And I had somebody last term in class who grew up in Pennsylvania, and he tells me it's a lot better now, but there are still parts of Pennsylvania that are problems when it comes to air pollution. This is the London smog of 1952. Now, it's not America, but still they were telling you before that a lot of countries, industrialized countries, had air pollution problems, and here is England, here is London in 1952. If you've seen The Crown, if you're a fan of that, there's an episode where they show the terrible fog issue. How much of that episode is true, I don't know, because they've taken a lot of liberties with history. But what is true is there were terrible fog problems in those days. I don't know if that whole subplot of them sneaking Winston Churchill into the hospital so he could visit people that were injured is true or not. And they showed him having his secretary killed in the fog, but people did get killed because this is daytime, and you can see that you can barely see anything. Again, this was, and we'll talk about the difference between fog and smog in a minute, but basically one is natural and one is not. This is man-made, which means if we stop certain behaviors, we can try and clean it up. This is showing us LA, Los Angeles, which we know is one of the worst cities, has some of the biggest problems with pollution control over the years. Look at it in 1968. Yes, I know the difference. The pictures are black and white versus color. Also, when you look at it, you can see the other difference is air quality has improved tremendously. Here is Delhi in India in 2014, still a big problem, still a lot of people. We've talked about, excuse me, talked about India before, and part of the problems they've had and why they've not been able to clean up their act, quite literally. That's some of the pollution problems that we've seen in many, many places, unfortunately, around the world. Okay, let me go back into the book. Hold on. There we go. So keep that in mind as we go along. Obviously, things had to be done. Your carbon oxides, another class of pollutants, and you know these, carbon monoxide, which is odorless, it's colorless, but it's a deadly poison. The reason it's so dangerous is it reduces the blood's ability to carry oxygen. Because in the normal scheme of things, your red blood cells are supposed to, when they get depleted, they take oxygenated blood to the lungs, and then they go and get some more oxygenated blood that's depleted, and it binds to the hemoglobin inside the red blood cells. But what happens though is, I think it's 40 times, if I remember my number correctly, and if I'm wrong, I apologize. I don't have it in front of me, but it's a much larger affinity, much larger likelihood for, if it's in the same room, carbon monoxide and oxygen. The carbon monoxide has a better chance to bind to the hemoglobin in your blood cells, which literally means you can become oxygen starved if there's enough carbon monoxide in the room, because what it does is it bonds with your red blood cells and it keeps the oxygen from binding to them, and you basically die because you become deoxygenated. So that's why carbon monoxide is so dangerous, and that's why they warn you about it. And a lot of times people do stupid things, and this happens a lot after you have a hurricane or a bad storm and the power goes out and people can't, if you have electrical appliances like I do and you don't have gas, so some people have a grill. So these people, these rocket scientists, take the grill inside the house. Now I'm talking about a coal-fired or gas-powered grill. One of the things that's produced is carbon monoxide. So people, well, I don't want to share it with my neighbors. So they lock the windows, close the doors, and you're producing this cloud of carbon monoxide or natural gas in your house, and you can kill yourself. And it's happened. And I remember after storms, when I worked for the health department, can't remember what storm it was, maybe it was Wilma, and we went around and we were knocking on doors and people would ignore us, and you could smell the hot dogs smelled good. And I think they thought we wanted hot dogs, and maybe we did. But our real reason, more of our reason for knocking on the door, is trying to keep people from killing themselves, trying to keep people safe, saving them from their own stupidity. And that's what happens if you use those things. Now, up north, we're not people that know anything about cold. At least I don't. I'm a native South Floridian. But if you're using heaters up north that are gas powered and you don't have proper ventilation in the house, you could really get into trouble. So they have recommended people buy CO, carbon monoxide detectors. When I worked in one school and I went through the dorms and I saw that we had, some of the dorms had stoves where we could cook, I said, you know what I want in these dorms? I want not just smoke detectors, I want a carbon monoxide detector. So we bought combined units because I was afraid that pilot light would go out and the gas would spread and people could get sick or die. So it's very important. And in some municipalities, when they know these situations are going to happen, fire departments or sometimes City Hall will give them out for free, carbon monoxide detectors, to reduce people getting injured or dying. So carbon dioxide is not something to play with. Carbon dioxide, you know more of. It's our waste product in our body when we breathe out. And remember, we've talked about this before, and that's one of the reasons it's so good to have plants outside. And I'll talk about this again in chapter 9 when we talk about global climate change in more detail. But one of the things that happens is that what we realize is that we want to get rid of that carbon dioxide. You don't want it trapped in with you. And when I've been called over the years for indoor air quality cases and people are feeling dizzy, one of the first things I do is put on the meter to see what the carbon dioxide level is, because that just means you're in a room where there's not enough circulation of fresh air and everybody's breathing back in either their own or their neighbor's carbon dioxide. And that can be a problem. So that's the carbon oxides. Then you have hydrocarbons. Hydrocarbons, again, a lot of these things are related to cars. This is from burning gasoline. It can have all sorts of health effects, a lot of them to your respiratory tract, and some of these things are carcinogens. They might cause cancer. And they definitely contribute to photochemical smog. We'll talk about what that is more in a minute, but that's not natural, that's from gas. And we'll see in the next chapter, methane is one of the global warming gases, one of the greenhouse gases. We'll see a list of them in a few minutes. All right, so you have methane, or as the British say, methane, When I say methane, which is CH4, otherwise called natural gas, and people make jokes about it when people pass gas, they go, oh, you're producing methane, which is true in small amounts. And methane, we want to obviously have fresh air circulating, but it's usually more outside methane. And then benzene, which is definitely carcinogenic, and it has kind of a sweet smell. And they used to use it as part of cleaning products, but they've reduced it because it's carcinogenic. Back when I took organic chemistry, we used to use benzene to clean certain materials because if you used water, the thing would literally melt. We would use these little plates that we'd have to put another chemical on and then put that into an apparatus. And if you tried cleaning these little plates that were made out of some sort of a salt compound, if you put it under the sink, it would melt in your hands. So you had to use benzene. But benzene was extremely dangerous. It was highly flammable and also carcinogenic. And I remember one of the persons in our class, she was pregnant. We would send her out because we didn't want her getting exposed to the benzene. And we'd do it under the fume hood, but still, it's not something to play with. Benzene, and if you ever take organic chemistry, benzene rings are very common, and it's one of the structures you will learn. If you're not, you can delete that from your memory. Ozone, the infamous ozone. Ozone is good and ozone is bad, depending where it is. Remember last lecture? If the ozone's in the stratosphere, what? The ozone's in the troposphere. The ozone's in the troposphere, it's a pollutant to ground level. In the stratosphere, it's a good thing because that's where the ozone layer is. That's where it helps to absorb UVA and UVB radiation. It is in the troposphere a component of photochemical smog. It's not good. It irritates our respiratory system and it hurts plants because plants do absorb this in many places and radiate it back. You'll see a picture later of how it radiates it back. So it's sort of like getting revenge on us, but it's not good. It's a pollutant. And it comes back as a pale blue gas with irritating odor. The Blue Ridge Mountains that have that distinctive blue color, a lot of that is from pollution from the plants around the mountain range absorbing ozone and reflecting it back at us. Then we have a whole category of HAPs, hazardous air pollutants. If I was teaching my air pollution class, we would go into more detail, but here we're only going to talk about a couple of them, but you should know there's quite a few of these. The list is always growing. Chlorine and formaldehyde are two very common ones. You've heard of chlorine. Chlorine comes in many forms. Here we're talking about the chlorine as a gas. It's a yellow-green gas, which is poisonous. It's not good either in the pool when it's used as a liquid, but it's a different sort of toxicity when you're talking about a liquid. This is more dangerous when you're talking about people who live close to chemical factories where they may be burning different chemicals and you get residue of chlorine, and formaldehyde is another one. Formaldehyde, people think of it for preserving bodies, which it is used for, although it's not used anymore. A lot of places they've gotten rid of formaldehyde to protect tissue, and it's used. They use other things. One place where I work, they use what's called Carolina mixture because the Carolina Biological Company makes that one. But there's other ones, I just call them all fake formaldehyde because the point is to preserve tissue. Every now and again, I've gotten called in where we have an old lab or somebody, we had a guy who was there for 45 years and he had an old set of specimens in bottles and these suckers had actual formaldehyde in them. And I had to get a company that was willing to get rid of formaldehyde because it's carcinogenic. And there's a whole way it has to be gotten rid of. So you don't want, and now believe it or not, formaldehyde's also in a lot of components and people like the smell of them and don't realize it because you only think of it in embalming fluid. It's also in, I'll say, cheaper carpet, like commercial grade carpet, that smell everybody loves in carpet. One of the things that you like in that smell and that compound and that chemical is the formaldehyde. And I'm no different. I like that smell of that commercial grade carpet. And for many, many years, I worked in rentals. And as an inspector also, we used to get exposed to that. So God knows what that will do to me over time, but I know that that's one of the more common, say, streams of it. This is showing you the ozone layer depletion. You see how it should work with the UVA and UVB. The ozone layer would shield the Earth. Over time, the CFCs, the chlorofluorocarbons, up into the air. They're made out of fluoride, chlorine, and carbons. That's why they're called chlorofluorocarbons. And these things munch away at parts of the ozone, which then lets more of the UVA and UVB rays get through. And some of the common ozone depleting chemicals, which we've gotten rid of a lot of these, were the CFCs. These were propellants for spray cans. They were very popular up into the 70s and 80s. Two countries that have a love affair with spray cans. One is the United States, but most people don't guess the other one right away, and it's Japan. I don't know exactly culturally why that is, but I know I've read a lot of articles about it, where the Japanese people, for some reason, love spray cans. In some countries, they just stopped using spray cans, but in the US, it became like a national priority in the late 70s, early 80s to find a different gas because we couldn't get our spray cans. Now, in self-defense, think of it. All of us that grew up with Ready Whip, whipped cream, it's nothing like spraying that into your mouth when your mother's not looking. My own kids have done it. My wife and I can't really yell at them because we did it too when we were kids. And then Cheese Whiz. I mean, could you want Cheese Whiz without being able to spray it? I mean, I don't eat that anymore, but when I did, come on. And we're just very much a spray-on society. So for a little while, they did ban it until they found the new gas, because people really, really love spray cans in this country. You can read the psychology of it somewhere else. You can Google that. I'm sure some of you out there going, that's interesting. And it is an interesting thing. Then you have the HCFCs. These is another type of CFC, which were used in refrigerants and industrial solvents. And some years ago, they made us bring in this type of Freon in our cars and in our air conditioners. And I remember I was driving an old piece of junk in the 90s. That was my first car, maybe it was my second car, but I still couldn't afford a new car. And I brought it in, and they had to take out the old, and they've been through various versions of the Freon. I just call it fake Freon. A lot of my classes, I've had auto mechanics that they send over from Sheridan Votech to take the class because they need it as a requirement, and they could always keep me up to date on what the most recent version of Freon is. And I'll say one, and they'll correct me. So I just ask them, because I sometimes get mixed up. But there have been many versions, and they got rid of them because they were ozone depleters. And obviously, we can't live without air conditioning, particularly down here. You're going to have to find replacement gases. Then there was halon gas. This was used in fire suppression systems for electronic equipment. So when I started out, if you had a computer room, the automatic sprinkler systems that came on, they weren't water with electricity. With computers in server rooms, they had halon, which is a foam that would come out and put out the fire. It's very messy. What they found out, though, was that halon, in addition to destroying the ozone layer, it also sucks the oxygen out of the air. So first responders had to be careful, and people leaving the building, because they sometimes would pass out because too much oxygen was removed from the air. You can only use this if your system had it originally. You can't build a new system with it. It's banned. And I have sold it, not for money for myself, but for places I've worked. They gave me money credit towards the more environmentally friendly gases. I could reuse the same pump system and the same nozzles, but I didn't want to use the halon gas. And then methyl bromides, which somebody just asked me about the other day, which are in pesticides, and somebody was worried it was getting into the water supply where they were. And when we tested the water, one of the things I tested for were bromides, including methyl bromides and hydrogen, sulfur, a whole bunch of things. But the main thing was the methyl bromides they were concerned about. So these are some of the other things you've got to worry about with the ozone depletion. Now, outdoor air pollution sources are kind of obvious to many people. Your two main sources, obviously transportation. Those are mobile sources because they move. Cars and trucks, construction equipment. And then your power plants, which are stationary sources, because in many places you're burning coal, you're burning oil, places used to burn wood. All these things release pollutants. And yes, we're doing pollution control. We'll talk about it in a minute, but still we're letting a lot of stuff into the air. Now, people who fight, and we'll see this in the next chapter when we talk about global climate change, people are always telling me, oh, but Professor, or oh, Mr. Shapiro, there is natural air pollution out there. And that's true. Volcanic eruptions produce sulfur dioxide all the time. Plants do radiate back ozone depleting gases, which I mentioned a minute ago. But when we'll talk about why there's a difference in this, even though that's true, it's only part of the picture. So your top sources of air pollutants outdoors, look at here, transportation, almost 60%. Miscellaneous, whatever that is, 10%. Fuel combustion, 20%, and industrial processes, 12%. So if you take transportation and fuel combustion, that's about 80% of your fuel consumption, which also leads to a tremendous amount of outdoor air pollution. Some of the biggest offenders are the chemical industry, metal industries, and paper industries. Then on top of that, we're knocking down trees because remember, the trees would pick up some of this carbon dioxide, or we're ramping up production of pollution, particularly the carbons and others, and we're destroying the trees at the same time. We've mentioned this before, it's not anything new. Some years ago, about 30 years ago, Mount Pinatubo in the Philippines erupted and released a lot of particulate matter. This is an example of a natural source of particulate matter, like I mentioned a minute ago. Now, a lot of people want to use this to argue against global climate change, which we'll see, but I'll just explain the logic. You can have global cooling because of aerosol deposition, which this is. When a lot of particles get into the air, it blocks the sunlight from penetrating through the cloud. And what you have is it actually gets cooler for a while underneath until that cloud breaks up. Oh, look, you're crazy. How can I'll show you a clip of Lisa Simpson in a few minutes and we'll get to chapter 9. How can you have cooling and warming and both be global warming? Well, that's why they don't call it global warming anymore. They call it global climate change because we have cooling and warming extremes. So for some years, we had after some of these incidents, months or years, sometimes years, depending how bad it was, you will have a general cooling effect in that area because of this aerosol deposition in the area. And that's a normal thing. This was Mount St. Helens. You see volcanic eruptions. And I said to you before, these happen every day. So to give you an idea, I put some numbers in here because people ask this. And this is not in your book. I just put it in because it interests me and I hope it interests you. Every volcanic eruption that occurs on planet Earth has pollutants in them. Not just acid, ashes and dust, mind you, but carbon dioxide, which we were talking about. This is one of the worst greenhouse gases on the planet. And in the largest cities, a single volcanic plume can last hours, but it can add millions and millions of tons of carbon dioxide to the atmosphere. So could it be the case then that individual volcanic eruptions add more carbon dioxide to our atmosphere than human activity does? I'm making that argument because this is the argument people make that are fighting with me against global climate change, that it's no better or no worse than natural phenomena that are already occurring. So just giving you some statistics. There are 33 measured degassing, that means volcanoes that are letting off gas, emitting a total of 60 million tons of CO2 every year. There are a total of around 150 known degassing volcanoes out there. So that comes to a total of 271 million tons of CO2 that are being released annually. The 30 historically active volcanoes, or 33 that are mentioned, are measured to emit a total of 6.4 million tons of CO2 per year. Now that sounds like a lot, and it is a lot. And you have to compare it to, so again, people will pull certain statistics that argue in their favor. I'm going to show you both sides because I want you to be aware of this. We'll see in a minute what the unnatural emission is. So we have 550 historically active volcanoes in total. They extrapolate this class of volcano, contributes about, let's say, 117 million tons of CO2 per year. Global total from volcanic lakes, there are some around the planet, another 94 million tons of CO2. Then we have emissions from plate shifts to tectonic shifts, hydrothermal activity, inactive volcanoes around there that still let out some CO2. It's another 66 million tons of CO2 a year. And then the mid-ocean underwater ridges have another 97 million tons of CO2. Again, this sounds big. You add all that up, comes to around 645 million tons of CO2. Whoa, what a number, right? 645 million tons of CO2 per year. Now, again, if you figure this out and compare it to humanity, let's say destructive use of different chemicals, the use that we make, humans make, is 29 billion tons per year. That's right, 29 billion tons. So if you convert 645 million using scientific notation into the decimal equivalent, it's 0.645 billion. It's not even a billion. If compare that number to the 29 billion, it's a fraction of it. So that tells us the majority of CO2 on this planet, I guess going back to the Industrial Revolution in the 1700s, comes from humans. So people will make this argument, and I'll talk about it again in chapter 9. All these things are occurring naturally every day on the planet. Yes, that's true. Volcanic eruption happens every day on the planet. Yes, that's true. There's millions and millions of tons of CO2 every year. Yes. First question. You're right. How much of that is, compare that to what humans release. Do you know how much humans make? How much do humans release per year compared to what the environment does during the year? We'll give you but it's 645 million. True. Compared to the figure I gave you a few minutes ago, which was 29 billion. Yeah, 645 million is a lot, but 29 billion is a lot more. So just to give you an example, so naturally, what would have to happen for nature to keep up with the, let's say, pace we've set? It would take 3 eruptions of Mount St. Helens every day and 1 Mount Pinatubo every day to equal the amount humanity is presently emitting. Mount Pinatubo does not erupt every day. Mount St. Helens certainly doesn't erupt 3 times a day. These are events that don't happen all that often. They happen, but they don't happen that often. So with the normal rate of eruptions, we're getting a fraction of what we humans produce. So that's what you have to look at as the overall number. Don't argue the fact that this doesn't happen naturally. It does. I'd be lying if I said it doesn't. So I'm trying to give you both sides. It does, but you got to look at the numbers. How much do we produce versus how much does nature produce? Okay. So now, what does air pollution do to us and other organisms? It injures us. It reduces visibility, which can lead to car accidents, among other things. It corrodes and destroys materials like we talked about before, metals and plastics and rubbers and the marble that we talked about. It can harm our respiratory tract and our immune system too, people don't realize. It can worsen especially heart conditions and other conditions, respiratory, pulmonary and respiratory conditions. It also, people don't think about this, it hurts crops because it affects plants' abilities to grow. So it affects crops, reduces their productivity. It's involved in acid deposition, global warming, and stratospheric ozone depletion. So this can be a big problem. Okay. Now, air pollution, low level of exposure may lead to eye irritation and respiratory tract inflammation. That's pretty much all air pollutants. It can hurt the immune system, and it can lead to or make worse emphysema, asthma, and bronchitis. And if you look here, you can go through all the things we just talked about, but you'll see that this is sort of a summary of what it can do to you. We have urban air pollution. That's pollution in the city. Sometimes we call it smog or industrial smog. The difference between fog is natural, smog is not. When you see fog, it's usually like a gray or a white. When you see smog, it's going to be, depending on which pollutant it is, it's going to be different colors. Smog is composed of sulfur oxides and particulate matter that we mentioned a minute ago, and it's usually worse in the winter. It's worse in the winter because we tend to burn more things in the winter because we're cold. And if we're not pollution controlling properly, we're releasing more particulates and other things into the air, exacerbating the problem. Plus, if it was summer or time of year where the sun was out, not here, but up north, the sun would help burn away some of the pollutants in the air. Industrial smog is worse in developing countries because as countries develop, one of the things that they want to do is have things that people in other countries have. And one of the first things everybody wants to get is a car. You're driving old cars that are not tuned up, that don't have any catalytic converters, don't have proper pollution control, which is going to lead to all sorts of issues when you're trying to control pollution. And now thousands, maybe millions of extra people buying cars leads to tremendous pollution. This happened in China, that even though the cars were small, they were buying literally compact cars, but there's a growing middle class and everybody wanted a car. So it was millions of additional cars on the road, even though each individual car might not be that bad. They were fairly good in terms of pollution control in China, but that many million extra vehicles on the cars on this road made it worse. In fact, one of the things that China tried doing when they had the Beijing Olympics, because they didn't want to admit how bad the air pollution was, they ordered millions of people not to drive for a couple of months to get the pollution levels down. You never get away with that in the United States, but you can do it in a country like China, and they did do it in a country like China, which artificially brought the pollution level down because they didn't want to be embarrassed. Imagine Summer Olympics and somebody's running and they're starting to have trouble breathing, and they go, oh my gosh, I would have done better if it wasn't in China. So they didn't want that, so they forced people to stop driving for a bit, and it cleaned up the air. And you may remember during COVID, and I was assigning last year during COVID, I was assigning articles about this. The air significantly cleaned up in many places because so many people were off the roads, and people were going, can we sustain this? Well, maybe if more people stay home, we can, but then you have the whole issue of, does telecommuting increase pollution or not? And I'll talk about that maybe a different day. But getting the cars off the road for a while, even a short while, definitely cleans up, at least for a while, the pollution. But then as soon as you start driving again like you were, then unfortunately the pollution levels come back. Photochemical smog is many times brownish or orangish or even reddish because their reactions. It's called photochemical because it's photo means not take a picture, but light. It's a light reaction. It involves sunlight, nitrogen oxides, and other hydrocarbons, and they become transformed from primary, which we talked about, the secondary pollutants later. The first noticed this in Los Angeles, it's still a problem, in the late 1940s when people really started driving after World War II in the late 40s, early 50s. It's worse in the summer months because the sun there's more of it. And since this is light dependent, the reactions that generate the smog, the more sun there is, the worse it gets. So that's photochemical smog as opposed to the urban smog, which is not photochemical. Ozone is a major component of photochemical smog. Again, ground level ozone. And it results in eye irritation and irritates the respiratory system, and it hurts plants. A lot of the sources are from cars, but people forget that dry cleaners, that's why they're starting to change chemicals in many places, release a lot of sulfur dioxides as well, and bakeries, believe it or not, from all of the baking. I remember as a kid walking down Washington Avenue in Miami Beach, and there was a bakery called Butterflake Bakery. I think it's still there, but you could, at a certain time of day, it smelled good. That's when they started up the bread and the pastry. And they would just blast all of this, I guess, remnants of the gases out a pipe. And part of it was to get people's attention. I want you to come and buy stuff in the bakery, and that's great. But you know what else happened? It was hurting. It's ozone depleting, and people don't realize that. Again, that was not because we're trying to hurt anybody. That was just trying to generate business. So going back to the different things that are formed, you see your sources of pollutants from cars, from factories, and it gets released, goes up into the atmosphere. And the nitrogen oxides and the sulfur dioxides and trioxides mix with oxygen and hydrocarbons and other oxygens, and you end up with nitric acids, ANS, formaldehyde, other aldehydes, and ozone. All these things we talked about before, all these atmospheric reactions. In addition, part of the other reason that some places have worse pollution than others are, let's say, accidents of geography. You notice Florida is not really an area that people have complained about air pollution. There's some, definitely, but not as bad as, let's say, New York City in the heyday. And that's because we're a peninsula. That means we're an island and we're open to the ocean. So air flows through and pushes a lot of the gases out. We may be poisoning somebody else, but Florida is not as bad as in some places. And we'll see what the worst city was in the 60s. I have a file on that. I'll go through that at the end of the chapter. Sometimes what happens over a city is we get what's called a temperature inversion. And what ends up happening is cold air traps a layer of cold air will trap pollutants under a layer of warm air and stay over a city. And we'll see a diagram of that in a minute. And this can lead to problems in places like Los Angeles, places like New York. If you're in a valley, you might have pollutants stick around. But if you're up in the mountains, the air is thinner, it might blow away. And if you're in some areas where, like the Los Angeles basin, cool air blows inland from the ocean, but the mountains around LA blocks it into the valley. And this allows warm, dry air to stay on top of the cooler air, and any pollutants that in it will stay over you. So right around the time when NEPA, remember that's the act that created EPA, this is when people were pushing for it, but even before there was an EPA, California was the first place to have and start enforcing emission levels from cars and having some sort of control of that. That's why we call it the CAFE standard. Another one of our environmentalist jokes, California Fuel Emissions Standard, CAFE, CAFE. So back in 1969, they were the first place really to do this. And then later, when we started doing that in other places, we were copying what California did, although California many times was stricter than a lot of other places because of their geography. The smog didn't go away. Now, the air is cleaner than it's ever been in California, but it's still out of attainment for EPA numbers, no matter what they do because of that. And the EPA recognizes that. and doesn't pound on them so hard because they know that California, of all places, has been trying for many, 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 many years to do something about this. Okay. This is showing you on top of a mountain, and we can study up there. And this is Mount Hua in China. They studied pollution is going to be a lot lower up in the mountaintop than it will be down in the valleys. So now this area, this idea of urban heat islands around areas around cities we talked about. Why do we get an urban heat island around a city and not so much in the countryside? Because you've got heat from sunlight is being absorbed by all sorts of different materials, artificial materials, which are typically more in the city. Think of asphalt and rooftops and street tops and glass and metal and all these materials that are constantly absorbing heat all day. And then it reflects it back at night. So this creates the areas in the cities are warmer than the country around them. And if you don't believe it, I remember as a kid going swimming, you get lazy, you get out of the car and you don't want to put on your sandals or whatever you got, and you step on that asphalt and your feet burn. And even hours later, you come out. I remember as a kid and as an adult, I'm wearing my sneakers. And I can feel the heat at night. I'm talking to somebody right in front of our house. I feel the heat coming back up out of the sidewalk or out of the street into my feet. Again, this has been absorbed all day and radiated back all night. So this is the urban heat island, and it's around the city. And it's not just the fact that it gets hotter, it also traps pollutants with it all over the city. Okay. All right. This is showing you how it gets hotter around the downtown. I might about a suburban area that's nearby. Why? Same thing, because there's more heat and it's trapped by all of these materials that are around the city. That's one of those things that people didn't realize. It seems very basic to all of us, right? But it's something people, for some reason, just didn't realize this all those years ago. It took people some years to figure this out. Okay, hang on a second. It's jamming up on me, which I do not want it to do. Come on, computer, don't do this to me. Why am I losing this? Hold on one second. Hold on, I'm having a problem here. Why is this not coming back up? Hold on. I'll be right with you. All right, it's jammed on me. Hold on. There it comes. All right, now let's see why it's doing this. If I can bring it back. All right, I don't know why it's doing this. Come on, computer. It's not letting me share. Okay, I think we're back now. All right. So the urban heat islands that we talked about before, wait a minute, share is not on now. Hold on a second. Where did that go? No, it's not. It stopped sharing. Hold on a second. All right, I may have to restart the computer. Stand by.